Greetings, dear friends. Today, we're setting off on an incredible journey across the vast reaches of our solar system. This is our home in space, a unique, dynamic, and astonishing system that formed billions of years ago and still guards countless mysteries. We'll discover how the solar system is arranged, where it sits in the universe, and why studying it matters so much to us. Get ready for a thrilling dive into science and history. We begin. The solar system is a grand gravitational mechanism, with our star, the Sun, at its center. It consists of 8 planets circling the Sun, more than 200 known moons, countless asteroids, comets, and interplanetary dust. All these objects are bound by gravity, forming a complex and harmonious structure. The scale of the solar system is hard to imagine. Including the Oort cloud, its diameter may reach nearly 2 light-years, about 19 trillion kilometers. Picture this. If the Sun were the size of a football, Earth would be 30 meters away, and only as big as a pinhead. Around 4.5 billion years ago, a massive cloud of gas and dust began collapsing under gravity. At its center, a dense core formed, the seed of the future Sun, which soon ignited through thermonuclear fusion. The remaining material created a spinning disk from which planets, moons, and other bodies gradually emerged. This process is the key to understanding how star systems form throughout the galaxy. Our solar system lies in the Milky Way galaxy, which contains between 100 and 400 billion stars. We're located in the Orion Arm, about 27,000 light-years from the galactic center. This is a relatively calm region, which likely played an important role in creating the conditions for life. Spiral arms are bright, winding regions of spiral galaxies filled with stars, gas, and dust. We sit between the larger arms of Perseus and Centaurus. This position offers relative safety because activity near the galactic core is far more intense. The solar system moves around the galaxy center at about 828,000 kilometers per hour. Yet a full orbit takes 225 to 250 million years, a galactic year. The last time we were in this part of the Milky Way, dinosaurs walked the Earth. Incredible as it may seem, if you could see our galaxy from the outside, the solar system would appear as a barely visible point among billions of stars. And yet, it's on this tiny point that life began, a phenomenon not yet found anywhere else in the universe. Let's look at how humanity's view of its place in the cosmos has changed. In ancient times, people believed Earth was the center of the universe. This idea was set out in Ptolemy's geocentric model, which dominated astronomy for nearly 1,500 years. According to this model, all heavenly bodies, including the Sun, Moon, and stars, revolved around Earth. But in the 16th century, a turning point arrived. The Polish astronomer Nicolaus Copernicus proposed that Earth is not the center of the universe, but just one of the planets orbiting the Sun. This became the basis of a new heliocentric model. Naturally, the idea met fierce resistance because it challenged centuries-old beliefs about humanity's place in creation. The next key stage is linked to Galileo Galilei. In the early 17th century, he used an improved telescope and for the first time observed the Moon in detail, revealing its craters and mountains. These observations shattered the notion of celestial bodies as perfect spheres. Galileo also saw the phases of Venus, a convincing proof of Copernicus's heliocentric model. These discoveries changed the foundations of astronomy. Later, in the late 17th century, Isaac Newton completed the picture with his laws of gravity. He explained why planets move in orbits around the Sun. Newton showed that gravity is a universal force, holding everything from the Moon to the farthest planets in their paths. His work became the foundation of classical mechanics and allowed astronomers to predict planetary motions with great precision. From the late 19th century, and especially in the 20th, a new era began, the age of practical space exploration. In 1969, the Apollo program first successfully sent humans to the Moon. And with the development of spacecraft and telescopes, people began actively exploring not only nearby planets, but also the most distant corners of the universe. The Hubble Space Telescope, launched in 1990, opened entirely new horizons. It gave astronomers incredibly precise data on stars, galaxies, and other cosmic objects. Thus, the journey from the old geocentric model to our modern scientific view of the cosmos has passed through crucial discoveries and revolutionary ideas. After tracing the milestones of astronomy and our understanding of the universe, let's now focus on the planets closest to the Sun, the so-called inner planets. They are Mercury, Venus, Earth, and Mars. This unique group of rocky worlds stands in sharp contrast to the giant planets of the outer solar system. We'll begin with the smallest yet very intriguing planet, Mercury. Mercury is the closest planet to the Sun, and everything about it is shaped by that proximity. It lies at a distance of about 39 astronomical units, a little less than half the Earth-Sun distance. Since one astronomical unit is roughly 150 million kilometers, Mercury orbits only about 58 million kilometers from the Sun. This makes it the very first planet in line from our star. Mercury is a dwarf among planets. Its diameter is about 4,800 kilometers, roughly 2.5 times smaller than Earth's. Yet despite its tiny size, it is denser than many other planets thanks to its massive iron core. A year on Mercury, its orbit around the Sun, is the shortest of all, just 88 Earth days. But its day, one rotation on its axis, lasts 59 Earth days. And because of a special interplay between rotation and orbit, a single solar day on Mercury, sunrise to sunrise, lasts nearly 176 Earth days. This strange effect is due to a spin-orbit resonance. For every 3 trips around the Sun, Mercury spins twice on its axis. Proximity to the Sun brings extreme temperature swings between day and night. By day, the surface heats up to about 430 C, hot enough to melt lead. At night, it plunges to 180 C. This contrast is among the most extreme anywhere in the solar system. Mercury is almost all metal. Its core takes up about 75% of the planet's diameter. Composed mostly of iron, and probably still partly liquid, it generates a weak magnetic field, about 100 times weaker than Earth's. Even so, this field creates a magnetosphere that interacts with the solar wind. Mercury's outer shell, its crust, is very thin, only about 20 kilometers. The surface is blanketed with craters from intense asteroid and meteoroid bombardment during the solar system's early years. One of the most striking craters is Caloris. More than 1,500 kilometers across, the impact that created it was so powerful, it produced chaotic terrain on the planet's opposite side. Our exploration of Mercury began with NASA's Mariner 10 mission in the 1970s. This spacecraft sent back the first detailed images of its surface and discovered the magnetic field. But the real revolution came with the Messenger mission, which entered Mercury's orbit in the 2000s. It gathered data on surface composition, measured the magnetic field, and revealed many geological secrets. Mercury is a window into the solar system's past. Its surface has barely changed for billions of years, preserving the marks of ancient planetary formation. Its structure and orbital behavior give scientists vital clues about gravitational interactions, the effects of stars on nearby planets, and how planetary cores cool over time. And now, our next mysterious world awaits: Venus. Conditions there are so extreme that it is rightly called the hellish planet. Venus is the second planet from the Sun and Earth's closest neighbor. In size and mass, it is astonishingly similar to our world, which is why it's often called Earth's sister. But the resemblance ends with the numbers. Venus is a true cosmic hell. Here reign unbearable heat, clouds of acid, and atmospheric pressure strong enough to crush any Earth-made probe in just minutes. Yet behind all this extreme environment lies a story that can reveal what might have happened to Earth if the balance of our planet had been disturbed. Venus has a diameter of about 12,000 kilometers, only 5% less than Earth's. Its mass is roughly 82% that of our planet, and its density and gravity are so similar that if you stood on Venus's surface, you would weigh almost the same as you do on Earth. Venus orbits about 72 astronomical units from the Sun, some 108 million kilometers. That's closer than Earth, but still not enough on its own to explain the planet's incredible heat. The real cause of Venus's catastrophic conditions is its unique atmosphere. Venus's atmosphere is among the most extreme in the solar system. It is made up of 96% carbon dioxide, with a little nitrogen and traces of sulfur compounds. Its upper layers are veiled in dense clouds of sulfuric acid that block direct sunlight. This is why Venus appears so bright and shiny in the night sky. Its clouds reflect up to 70% of incoming sunlight. Beneath those clouds lurks staggering pressure, 92 times higher than on Earth. It's equivalent to being submerged a full kilometer beneath the ocean. Any base or station built there would be crushed almost instantly. Venus's surface is the hottest of any planet in the solar system, reaching about 470 degrees Celsius. That's even hotter than Mercury, though Venus is farther from the Sun. The main reason is a runaway greenhouse effect that completely transformed the planet's atmosphere and climate. Long ago, Venus probably had conditions more Earth-like. It may even have had liquid water on its surface, but its closeness to the Sun and the high level of solar radiation caused temperatures to rise. Water evaporated, and the resulting water vapor, a powerful greenhouse gas, trapped even more heat. To this was added carbon dioxide, released in large amounts by volcanic activity. It accumulated in the atmosphere, increasing its density and amplifying the greenhouse effect further. Today, Venus is a planet-sized heat trap. About 70% of the Sun's light is reflected by its clouds, but the remaining 30% penetrates downward, is absorbed by the surface, and can no longer escape back into space through the thick carbon dioxide blanket. This process makes Venus the perfect thermal trap. Temperatures on the planet are almost uniform everywhere. There's little difference between day and night, or between equator and poles. That's because the dense atmosphere evenly distributes heat. Even at night, when the sun no longer shines on the surface, the temperature stays nearly as high as in daytime. Beneath this atmosphere lies a fascinating world. The surface has been mapped by radar, because ordinary optical observation is impossible through the thick clouds. Venus is a planet of volcanoes. Its surface is almost entirely covered by lava plains, created by past eruptions. One of its tallest features is the Maxwell Mountains, which rise about 11 kilometers high, taller than Mount Everest on Earth. Yet most of Venus's surface is flat, marked by strange geological formations such as coronae, huge circular structures formed by upwelling magma. These coronae are traces of powerful tectonic processes that took place billions of years ago. And still, despite the volcanoes and lava, Venus shows no clear signs of plate tectonics like Earth's. Instead, its crust seems to bend and break under the pressure of magma, creating a landscape unlike any other in the solar system. At about 60 kilometers above Venus's surface, unbelievably powerful winds blow, reaching up to 360 kilometers per hour. This phenomenon is called superrotation of the atmosphere. The atmosphere spins around the planet far faster than the surface itself. Venus takes 243 Earth days to complete one rotation on its axis, the slowest day of any planet. Yet its year lasts only 225 days. This means a single day on Venus is actually longer than its year. Venus was one of the first planets to be studied with space probes. The Soviet Venera missions were the pioneers, sending landers to its surface. Spacecraft like Venera 7 transmitted data from the ground, but survived no more than 30 minutes under the crushing heat and pressure. Later, the European Space Agency's Venus Express mission explored the planet's atmosphere and dynamics, including the chemical makeup of its clouds. Today, new missions are planned. NASA's Da Vinci and Veritas, which will study Venus's terrain and its inner structure. These investigations aim to answer a central question. Could Venus have been habitable in the past? And now we turn to our own planet, Earth. We'll discover what makes it unique and why it remains the only known home for life. The single most important feature that sets Earth apart is the presence of liquid water. About 70% of our planet's surface is covered by oceans, seas, and rivers. Water is the foundation of life. Its unique properties, such as high heat capacity and its ability to dissolve substances, make it perfect for sustaining biological processes. But why does Earth have liquid water, while Venus or Mars do not? The secret lies in its location. Earth sits in the so-called habitable zone, the region around a star where temperatures allow water to remain liquid. If Earth were slightly closer to the Sun, it might have shared Venus's fate. If it were farther away, it would have turned into a frozen desert like Mars. Equally important is the magnetosphere, Earth's magnetic field that shields our planet from the solar wind and cosmic radiation. It's generated by the motion of liquid iron in Earth's core and acts as an invisible shield. Without it, the solar wind could strip away the atmosphere, as happened on Mars. And what exactly is the solar wind? It's a stream of charged particles constantly released by the Sun. They flow outward from its hot outer layer, called the corona, traveling up to 800 kilometers per second and spreading through the entire solar system. The solar wind interacts with planets, creating different effects. On Earth, it produces the auroras and simultaneously collides with the magnetosphere, which protects us from its destructive force. Earth is a dynamic planet. Its surface is constantly reshaped by plate tectonics. The crust is divided into several large and small plates that float on the liquid mantle beneath. These plates move, collide, and separate, forming mountains, oceanic trenches, and causing earthquakes. Plate tectonics plays a key role in cycling materials on the planet. For example, carbon dioxide released by volcanoes helps maintain the greenhouse effect necessary to retain heat. Plate movement also renews the crust, supporting long-term stability of Earth's systems. Volcanoes, despite their destructive power, supply new materials to Earth's surface. They release gases such as carbon dioxide and water vapor that influence climate, and minerals that enrich the soil. Earth's atmosphere is another unique feature. Its composition is perfectly suited for sustaining life. The main components are nitrogen, about 78%, oxygen, about 21%, plus small amounts of carbon dioxide, argon, and other gases. This balance did not appear by chance. It was shaped by billions of years of biological and geological processes. Oxygen entered the atmosphere thanks to ancient microbes that released it during photosynthesis. This event, known as the Great Oxidation Event, happened about 2.5 billion years ago. It completely transformed the chemical makeup of the atmosphere and made Earth hospitable for complex life. Carbon dioxide, though it makes up only a small fraction of Earth's atmosphere, plays a key role. It regulates the planet's temperature through the greenhouse effect, preventing Earth from freezing. This delicate balance keeps the climate comfortable for life. But it is also vulnerable. Any major change in carbon dioxide levels could trigger climate catastrophes, as happened on Venus. Speaking of our planet, we cannot overlook its faithful companion, the Moon. The Moon is far more than just a beautiful object in the night sky. It plays a crucial role in Earth's stability and the development of life. The Moon's diameter is about 3,470 kilometers, making it the largest satellite in proportion to its planet in the entire solar system. First, the Moon stabilizes Earth's axial tilt. Because of it, the tilt stays relatively constant, ensuring stable seasons and climate. Without the Moon, Earth's axis could wobble dramatically, causing extreme climate shifts. Second, the Moon drives tides. These rhythmic movements of water in oceans, seas, and rivers not only shape coastal ecosystems, but may have been vital to the evolution of life. Scientists believe tides helped life transition from water to land, providing organisms with environments to adapt to new conditions. Third, the Moon acted as a cosmic shield for Earth, absorbing impacts from asteroids and meteoroids in the early solar system. Without it, our planet's surface might be far more heavily cratered. By studying the Moon, we not only understand Earth's uniqueness, but also see the fragility of our home. The next planet we'll explore is Mars, our close neighbor, capable of telling us about Earth's past and its possible future. Mars has fascinated humanity since ancient times. Its reddish glow in the night sky inspired myths and associations with war and destruction. But today, Mars represents not war, but hope. It has become a window into the solar system's past, and perhaps into humanity's future. Let's see why Mars draws such intense interest. Mars is the fourth planet from the Sun. It lies at an average distance of 228 million kilometers, or about 52 astronomical units, nearly 1.5 times farther from the Sun than Earth. As a result, Mars receives much less heat and sunlight. In size, Mars is about half of Earth, and its total surface area is roughly equal to all the land on our planet combined. Its mass is just 11% of Earth's, and surface gravity is about 38% of what we experience here. That means if you weigh 70 kilograms on Earth, on Mars, you'd weigh only 26. Mars is a frozen desert. Its average temperature is 63 C. But depending on season and location, it can range from 125 C at the poles in winter to pleasant 20 C near the equator in summer. These dramatic swings are due to its thin atmosphere, which barely traps heat. Mars's atmosphere is extremely thin. Surface pressure is only 0. 6% of Earth's, equivalent to conditions 30 kilometers above Earth's surface, about 3 times higher than commercial planes fly. It is 96% carbon dioxide, with small amounts of nitrogen, argon, and traces of oxygen and water. One of Mars's most striking features is its dust storms. They can engulf the entire planet. These storms lift fine dust into the atmosphere, block sunlight, and make Mars even colder. The largest recorded storm, in 2018, lasted for months and ended the mission of the rover Opportunity. Yet Mars's surface is astonishing. Its rusty plains, giant volcanoes, ancient dried riverbeds, and polar ice caps tell the story of a planet that may once have been very different. Imagine Olympus Mons, the tallest volcano in the solar system, rising 22 kilometers high. That's 3 times taller than Mount Everest. Its base is so vast that standing at its foot, you wouldn't even see the summit. Or picture the Valles Marineris, a colossal canyon system stretching 4,000 kilometers and plunging up to 7 kilometers deep. It's 10 times longer than the Grand Canyon and 4 times deeper. Scientists think these structures may have formed through tectonic processes, or perhaps from ancient water flows that once carved their way across Mars. Yes, water is the key to Mars's mystery. Today, there is no liquid water on its surface, but everywhere we see traces of its past presence. Billions of years ago, Mars was warmer and its atmosphere was denser. Rivers flowed here, lakes formed, and perhaps even an ocean covered a significant part of the surface. Now, water on Mars exists only as ice, in the polar caps or beneath the ground. However, there is a strong possibility that beneath the frozen soil lie underground lakes of liquid water, especially near the South Pole. These findings give hope that life might once have existed on Mars, and perhaps even hides there now. Today, Mars is the main target of space exploration. Rovers such as Curiosity and Perseverance continue to study its surface, gathering data on the climate, soil composition, and signs of ancient life. Curiosity, operating since 2012, confirmed that Mars was once suitable for life. And Perseverance, which arrived in 2020, is exploring Jezero Crater, the site of an ancient lake and river delta where microbial life could once have thrived. But our ambitions don't stop there. Elon Musk and his company SpaceX dream of sending humans to Mars within the coming decades of the 21st century to begin creating the first settlements there. Our next stop will be Jupiter, the king of planets, which reveals to us a completely different cosmic world. Between Mars and Jupiter stretches the asteroid belt, a region filled with millions of rocky and metallic objects that never coalesced into a full-fledged planet. Scientists believe Jupiter's gravity, the strongest of any body in our system after the Sun, prevented this from happening. And here we meet Jupiter, the largest and most mysterious planet in the solar system. It is so huge it could hold more than 1,000 Earths inside it. Its influence extends far beyond its orbit. This gas giant governs the movement of moons and acts as a kind of cosmic shield, pulling in asteroids and comets that might otherwise threaten Earth. Jupiter is a world of storms. Devastating hurricanes, monstrous pressures, and magnetism stretching across millions of kilometers. You cannot imagine it without its eternal great red spot, its incredible auroras, and its 4 largest moons, each of which could be considered a planet in its own right. Jupiter's mass is 318 times that of Earth. But if it kept accumulating matter, it would not get larger. Under its own gravity, it would compress into an even denser sphere. Gravity on Jupiter is 2.5 times stronger than on Earth. This means a person weighing 70 kilograms on Earth would weigh over 170 here. Of course, you couldn't stand on a solid surface. There simply isn't one. Jupiter consists mainly of hydrogen and helium, much like the Sun. Its atmosphere is a boiling ocean of gas. First come the upper layers, rich in ammonia and methane, where hurricanes rage across thousands of kilometers. Deeper down, hydrogen turns from gas into liquid, and then into metal. Such a state can be reached on Earth only in laboratories under crushing pressures. Here it forms an ocean of metallic hydrogen, tens of thousands of kilometers deep. It behaves like a metal and conducts electricity. It is within these layers that Jupiter's unbelievably powerful magnetic field is born, extending for millions of kilometers. What lies even deeper? Perhaps a small rocky core the size of 10 Earths, but scientists still debate this. Under immense pressure, that core may have partially dissolved into the liquid hydrogen. Jupiter's atmosphere is striking. It is covered with characteristic bands, light and dark zones. They are the result of powerful winds blowing in opposite directions at speeds up to 600 kilometers per hour. In this churning environment, lightning flashes thousands of times brighter than on Earth, and the pressure in the lower layers squeezes gas into liquid. And of course, we cannot ignore the Great Red Spot, a gigantic hurricane raging for at least 350 years. Today, its diameter is about 16,000 kilometers, several times the size of Earth. And that's already smaller than it once was. The spot is gradually shrinking. Scientists do not yet know whether it will disappear completely someday. But this storm remains one of the most awe-inspiring phenomena in the entire solar system. Jupiter's magnetic field is the most powerful of any planet. It is 20,000 times stronger than Earth's. Its giant magnetosphere is so vast that if we could see it, it would cover more of the sky than the Moon. Jupiter is a true radiation hell. Streams of charged particles rage around it, and the radiation in its vicinity is lethal even for the most heavily shielded spacecraft. That is why missions such as Juno are forced to perform complex maneuvers to avoid the most dangerous zones. But Jupiter is not just the gas giant itself. It has more than 80 moons, and the most famous of them are the 4 Galilean satellites: Io, Europa, Ganymede, and Callisto. Each one is a world of its own, with its own history and unique features. Io is a volcanic inferno, the most geologically active object in the solar system. Its surface is covered in sulfur, which gives the moon a bright yellow color. Io's interior is heated by the gravitational tug-of-war between Jupiter and the neighboring moons. Europa is a world beneath the ice. Its surface is covered by an ice shell several kilometers thick, and beneath it lies an ocean of liquid water. And not just any ocean. Its volume is greater than all of Earth's oceans combined. Cracks caused by Jupiter's tidal forces scar Europa's surface, and geysers shoot plumes of water straight into space. If life exists anywhere in the solar system beyond Earth, Europa is one of the top candidates. Ganymede is the true king of moons. It is larger than the planet Mercury, and is the only moon in the solar system with its own magnetic field. Its surface is covered with ice and ancient craters, and deep inside it probably hides a subsurface ocean. Callisto is an ancient, cratered world. It is one of the oldest objects in the solar system, and its surface has changed little over billions of years. Beneath its icy crust, like Ganymede, there may be an ocean as well. Jupiter was the first planet to be studied up close. In the 1970s, it was visited by Pioneer and Voyager, in the 1990s by the Galileo mission, and today Juno continues to operate there. The future exploration of Jupiter promises to be even more exciting. In the 2030s, the JUICE mission will head to Ganymede and Europa to find out whether life could exist in their oceans. Jupiter is rightly called the king of planets. But its neighbor Saturn is no less astonishing. It is a world that seems like the embodiment of alien beauty, surrounded by the greatest ring system in the solar system and blessed with remarkable moons. After Jupiter, our journey takes us farther, to Saturn, a planet that is truly one of the most beautiful in the solar system. If Jupiter can be called the king for its size and power, then Saturn is its aristocratic brother, encircled by the most spectacular rings that make it unique. Saturn is the second largest planet in the solar system. Its diameter is 120,412 kilometers, almost 10 times the diameter of Earth. Yet despite its enormous size, Saturn remains the lightest planet. Its average density is less than that of water. This means that if a large enough ocean existed, Saturn would float in it. But its main adornment is its rings, which have made Saturn one of the most recognizable planets. In photographs, they look dense and solid, like a single solid disk. But that is an optical illusion. In reality, the rings consist of billions of ice and rock particles orbiting the planet. Their sizes range from tiny dust grains to chunks as large as houses. The thickness of the rings is astonishingly small compared to their width, only about 10 meters on average, while their diameter stretches hundreds of thousands of kilometers. They are essentially a gigantic flat disk so thin that from the side it nearly disappears. Scientists still debate their origin. They may be the remnants of a destroyed moon that ventured too close to Saturn and was torn apart by gravity. Or they may be material that never managed to coalesce into a full-fledged satellite. Within the rings are remarkable structures. For example, the Cassini division, a vast gap about 4,800 kilometers wide that splits the rings in two. The culprit is the moon Mimas, whose gravitational influence literally sweeps particles out of this region. Like Jupiter, Saturn's atmosphere is composed mainly of hydrogen and helium, with traces of other gases that give the clouds their yellow and golden hues. But where Jupiter draws attention with its great red spot, Saturn has an equally mysterious feature, the hexagonal storm at its north pole. This is a genuine scientific phenomenon, a gigantic hurricane 25,000 kilometers across, shaped like a perfect hexagon. Inside it, winds rage at over 500 kilometers per hour, and the edges of the storm remain astonishingly sharp, as if drawn with a ruler. Scientists still do not know why the hurricane takes this shape, and it is not the only atmospheric phenomenon on Saturn. In 2010, the planet's northern hemisphere suddenly changed color, from bluish to golden. This happened because of photochemical reactions triggered by sunlight. When summer arrived in that region, ultraviolet light broke apart the molecules that gave the atmosphere its blue tint, and the clouds took on a new golden hue. Saturn is not just the planet itself, but also its 83 moons, and among them, one stands out above all: Titan. This is one of the most extraordinary worlds in the solar system. Titan, the second largest moon after Ganymede. It is bigger than Mercury and the only moon with a dense atmosphere. It is this atmosphere that makes Titan so special. If you were standing on Titan's surface, the sky above you would be orange-yellow, and around you would stretch plains covered with frozen hydrocarbons. Most astonishing of all, it rains here, but not water. Liquid methane and ethane fall from the clouds. The temperature is about minus 180 degrees Celsius, so water on this world is hard as rock. Its rivers, lakes, and seas consist of hydrocarbons, which remain liquid under these conditions. In many ways, this world is strikingly reminiscent of Earth. It has seasons, clouds, and precipitation. Its rivers and lakes change with the seasons. Some methane seas slowly evaporate, while new ones appear elsewhere. But the most intriguing possibility lies deep beneath Titan's surface, a hidden ocean of liquid water. If that is true, then conditions suitable for life may exist there. If Titan amazes with its atmosphere, another of Saturn's moons, Enceladus, stuns with its geysers. This tiny world, only 500 kilometers across, turned out to be incredibly active. NASA's Cassini spacecraft discovered powerful jets erupting from Enceladus's south pole, hurling plumes of particles into space. They are so intense that one of Saturn's rings is made from them. Beneath Enceladus's surface lies an ocean of liquid water, and within the plumes, scientists have detected organic molecules and chemical reactions that could provide energy sources for life. All of this makes Enceladus, alongside Europa, one of the prime candidates for extraterrestrial life in the solar system. The most detailed exploration of Saturn and its moons came from the Cassini-Huygens mission. Launched in the 1990s, it spent 13 years in the Saturn system, returning thousands of images and unique scientific data. The Huygens lander separated from Cassini and descended to Titan, becoming the first spacecraft to land on the surface of a moon belonging to another planet. It sent back images of the orange haze, rocky plains, and traces of ancient rivers. In 2017, Cassini ended its mission, plunging into Saturn's atmosphere while transmitting data until the very last moment. Saturn is the last of the gas giants, but beyond it lie Uranus and Neptune, the ice giants, worlds that hold no fewer secrets. They have the most powerful winds, strange magnetic fields, and moons where subsurface oceans may also hide. After traveling through Saturn's realm, our path continues deeper into the solar system, into the domain of the ice giants. Uranus is the seventh planet from the Sun. Although it is smaller than Jupiter and Saturn, its uniqueness is astonishing. It is a blue, mysterious world that spins on its side, encircled by rings and moons with remarkable terrain. Its cold, harsh atmosphere conceals mysteries that remain little explored. Like Jupiter and Saturn, Uranus belongs to the category of gas giants, but with a crucial difference. While the two largest worlds consist mostly of hydrogen and helium, Uranus and its neighbor Neptune belong to another class, the ice giants. Uranus contains much larger amounts of heavier elements, water, ammonia, and methane. Instead of hot metallic hydrogen as in Jupiter, Uranus has a vast layer of ice made of these substances deep within. If you were to descend into Uranus's atmosphere, you would first pass through upper clouds of methane and hydrogen. Then the pressure would rise, and the gases would compress into liquid and icy layers. But if you ask whether Uranus has a solid surface you could stand on, the answer is no. Its atmosphere merges gradually into deeper layers, and the surface can only be defined as the level where the pressure matches that at Earth's sea level. At Uranus's center, there is probably a rocky core about the size of Earth, wrapped in a thick layer of hot icy mantle. Temperatures inside may reach 5,000 degrees Celsius, yet because of the powerful icy layer, the heat barely escapes. That is why Uranus is one of the coldest planets in the solar system. Its average temperature is about minus 224 degrees Celsius, making it even colder than the more distant Neptune. Why is that? Unlike the other giants, Uranus releases almost no internal heat. But the most remarkable thing about Uranus is its unusual rotation. Unlike every other planet, Uranus's axis is tilted by 98 degrees. It literally rolls along its orbit. Its poles point directly at the sun for decades, then plunge into total darkness. This creates the most extreme seasons in the solar system. Where Earth switches between winter and summer every 6 months, Uranus has one pole facing the sun for 42 years, followed by 42 years of night. Scientists believe that during its early formation, Uranus was struck by a giant object, perhaps a planet the size of Earth. This collision altered its axial tilt, and now Uranus spins completely differently from all the others. Although Uranus appears to be a calm blue sphere, its atmosphere is anything but tranquil. It is composed mainly of hydrogen, helium, and about 2% methane. It is methane that gives the planet its blue color, because it absorbs red light and reflects blue and green. On Uranus, some of the strongest winds in the solar system blow, reaching speeds of up to 900 kilometers per hour, even faster than the most powerful hurricanes on Earth. At times, gigantic cloud formations appear, stretching for thousands of kilometers across the atmosphere. Although rings are most often associated with Saturn, Uranus has rings as well. They are much thinner and darker, made of particles that reflect very little light. But the planet's greatest wonders lie among its 27 moons. The most extraordinary of them is Miranda. This moon looks as if it's been shattered. Its surface is carved with massive faults, cliffs, and chasms. Some of Miranda's canyons are deeper than the Grand Canyon on Earth. Scientists believe Miranda may once have been torn apart by a powerful collision, after which its fragments reassembled, creating this chaotic world. So far, the only spacecraft to visit Uranus has been Voyager 2. In 1986, it flew past the planet, sending back the first, and still the only, close-up images. Since then, no mission has returned to Uranus. However, scientists are planning new explorations. Perhaps in the 2030s, NASA will send a probe capable of studying the atmosphere, moons, and internal structure of this mysterious planet in detail. After the cold and enigmatic Uranus, our journey reaches the last of the known giants of the solar system, Neptune. It is the most distant, the windiest, and perhaps the most mysterious planet. Even today, with modern telescopes and computer models, Neptune remains one of the least explored worlds. At first glance it resembles Uranus, a bluish sphere hidden beneath layers of clouds. But the difference soon becomes clear. If Uranus is a quiet, frozen world, Neptune is a raging storm giant, where the most powerful hurricanes in the solar system rage. Neptune is an ice giant like Uranus, but its atmosphere is more dynamic and active. It consists of hydrogen, helium, and methane, and its blue color is also caused by methane. But the defining feature is the wind. Neptune's atmosphere hosts the strongest storms in the solar system, winds reaching 2,400 kilometers per hour. That's faster than the speed of sound in Earth's atmosphere and 3 times stronger than the most destructive hurricanes on our planet. Scientists still do not fully understand how Neptune sustains such a violent atmosphere. The planet receives only 1/9 the sunlight that Jupiter does. Its upper layers seem cold and calm, but deeper down rages a true inferno of storms and vortices. Neptune even has its own massive hurricane, the Great Dark Spot. When Voyager 2 sent back the first images in 1989, scientists saw a huge feature reminiscent of Jupiter's Great Red Spot. It stretched 8,800 kilometers across, with wind speeds of 2,000 kilometers per hour inside it. But a few years later, when astronomers observed Neptune again using the Hubble Space Telescope, the spot had vanished. It simply dissipated. Later, new dark spots were discovered, other giant storms that appear and disappear every 5 to 10 years. This makes Neptune unique. Here, storms do not last for centuries, but come and go within mere decades. Like Uranus, Neptune has no solid surface. If someone tried to land there, they would simply sink deeper and deeper into the layers of gas until the crushing pressure destroyed them. Unlike the gas giants Jupiter and Saturn, Neptune contains more ice and heavier compounds: water, ammonia, and methane. Beneath its dense atmosphere lies a thick icy mantle, and beneath that a hot, dense core of rock and metal. The temperature at Neptune's center may reach 7,000 degrees Celsius. This core emits twice as much heat as the planet receives from the sun, and it is this internal energy that drives Neptune's fierce winds and atmospheric activity. Among Neptune's moons, one stands apart: Triton. It is the planet's largest moon and one of the strangest objects in the solar system. Its most remarkable trait is that it orbits in the opposite direction to Neptune's rotation. This means Triton did not form with Neptune, but was captured by its gravity from the Kuiper Belt, a region of frozen bodies beyond Neptune's orbit. And the oddities don't end there. Triton's surface is covered with nitrogen ice, and the temperature is about minus 235 degrees Celsius, one of the coldest places in the solar system. But the most astonishing discovery is its icy geysers. Voyager 2 detected enormous plumes of nitrogen erupting from Triton's surface. This indicates a hidden source of heat deep inside, warming the ice and causing it to vaporize. Some scientists suspect that beneath Triton's icy crust, there may be a subsurface ocean of liquid water, like on Europa or Enceladus. For now, Voyager 2 remains the only spacecraft ever to visit Neptune. No new missions have followed yet, but in recent years, astronomers have been discussing the possibility of sending a probe. One concept is Neptune Odyssey, an orbiter that could study the planet in detail. NASA is also considering a mission called Trident, which would head to Triton to test the hypothesis of a subsurface ocean. But such expeditions take decades. Even if a probe were launched soon, it would not reach Neptune until the 2040s. Our journey through the planets of the solar system ends here, but the solar system itself does not. Beyond Neptune stretches the Kuiper Belt, a region filled with thousands of icy worlds. Pluto, Haumea, Makemake, and many others. We have traveled through all 8 planets, but between them and beyond them lies an entire realm of small bodies, asteroids, comets, dwarf planets, and meteoroids. These objects may seem insignificant compared to giants like Jupiter or Saturn. Yet their role in the formation and evolution of the solar system is immense. They preserve information about its distant past, and some even pose potential hazards to Earth. When astronomers first began systematically scanning the sky, they expected to find another planet between Mars and Jupiter. By the laws of celestial mechanics, a large world should have been there. But instead of a single planet, they discovered an entire asteroid belt. A zone filled with millions of bodies that never coalesced into a planet because of Jupiter's gravitational influence. Asteroids come in all sizes, from giants like Vesta, about 525 kilometers across, to tiny fragments just a few meters wide. They are made of metals, silicates, and carbon compounds, and some even contain water. But beyond scientific interest, asteroids also pose a real threat to Earth. We know that 66 million years ago, one of them struck our planet, triggering the mass extinction of the dinosaurs. Today, astronomers closely monitor potentially hazardous asteroids capable of crossing Earth's orbit. The largest of them are currently safe, but even smaller objects can present a danger. That is why NASA and other space agencies are developing defense methods, including missions like DART, which in 2022 successfully changed the orbit of a small asteroid. For a long time, Pluto was considered the 9th planet of the solar system. But in 2006, astronomers reclassified it as a dwarf planet. This sparked heated debates because for many people, Pluto had always remained a full-fledged planet. Why was it demoted? The reason is that Pluto does not dominate its orbit. Around it are other objects, such as Haumea, Makemake, and Eris, which could also be considered planets. All of them are located in the Kuiper Belt, a vast region beyond Neptune filled with icy bodies. Yet despite this, Pluto remains an extremely interesting object in the solar system. It has 5 moons, the largest of which is Charon. Charon is so large compared with Pluto itself that together they form a double system, orbiting a common center of mass. Pluto's surface is covered with icy plains and cryovolcanoes. When the New Horizons probe flew past Pluto in 2015, it sent back images that amazed scientists. This small world turned out to be far more complex and active than expected. If asteroids are mostly made of rock and metal, comets are dirty snowballs of ice and frozen molecules. As they approach the sun, they begin to sublimate, forming a tail. This tail always points away from the sun, shaped by the solar wind. Comets come from 2 regions. The first is the Kuiper Belt, the nearest source of short-period comets, such as the famous Halley's Comet, which returns every 76 years. The second is the Oort cloud, a giant sphere at the edge of the solar system from which long-period comets arrive. For example, Comet Hale-Bopp. Comets played a key role in Earth's history. Some scientists believe they may have delivered water to our planet, and possibly even organic molecules needed for the origin of life. And what about meteorites? They are small fragments of asteroids or comets that fall to Earth. Most burn up in the atmosphere, creating the effect of a shooting star. But some reach the surface. The most famous recent example is the Chelyabinsk meteor. In 2013, it entered the atmosphere, produced a shockwave, and shattered thousands of windows in the city. Our journey through the planets of the solar system is coming to an end. When you think about it, everything we have seen, from tiny Mercury to giant Neptune, exists thanks to one object. Without it, there would be no warmth, no light, no orbits, and certainly no life. That object is the Sun, our stellar source of energy around which the entire system revolves. The Sun is a star. It is not just a hot ball, but a complex, dynamic world where nuclear reactions continuously generate colossal amounts of energy. It holds 99% of the total mass of the solar system. This means that all the planets, moons, asteroids, and comets together weigh less than 1/100th of the Sun. But what exactly is this gigantic light giver? What processes occur inside it, and how does it affect our planet and the entire system? Let's find out. The Sun seems to us like a solid glowing sphere, but in reality, it consists of several layers, each playing a role in generating and transporting energy. The core is the Sun's center. This is where the most important processes take place. The temperature reaches 15 million degrees Celsius, and the pressure is 250 billion times greater than on Earth. Under these hellish conditions, thermonuclear fusion occurs. Hydrogen atoms fuse into helium, releasing a colossal amount of energy. The radiative zone comes next. Here, the energy produced in the core slowly moves outward in the form of radiation. Photons born in the depths of the star can travel through this layer for tens of thousands, even millions, of years before reaching the surface. The convective zone works differently. Here, energy is carried by powerful currents of hot plasma, like in a boiling pot. These flows create granules and sunspots on the Sun's surface. The photosphere is a thin layer only about 500 kilometers thick, the part we see from Earth. It emits the light that warms and illuminates our planet. Its temperature is about 5,500 degrees Celsius. Above it lie the chromosphere and the corona, the outer layers. The corona is a vast, superheated cloud of plasma extending millions of kilometers into space. The Sun is an active, living star. Every second, billions of tons of hydrogen are transformed into helium, releasing energy equal to the explosion of billions of hydrogen bombs. This process keeps the Sun stable and allows it to shine for 5 billion years. But it is not always calm. Sometimes powerful flares erupt, throwing vast amounts of charged particles into space. When such flares are directed toward Earth, they cause geomagnetic storms. Even more dangerous are coronal mass ejections, gigantic blasts of billions of tons of plasma racing through space at hundreds of kilometers per second. If they hit Earth, they can disrupt satellite communications and even power grids. Despite its great distance from the outer planets, the Sun's influence is felt throughout the solar system. The main mechanisms of this influence are gravity, radiation, and the solar wind. The Sun's gravity holds all the planets in their orbits. Without it, they would immediately drift off into interstellar space. Its radiation provides Earth with heat and light, sustaining life. Without it, our planet would freeze into a lifeless, icy sphere. The solar wind, a stream of charged particles, interacts with planetary magnetic fields to create auroras. The most distant boundary of the Sun's influence is the heliopause, where the solar wind collides with interstellar space. This is about 20 billion kilometers from the Sun. Beyond it lies interstellar space. The Sun has been shining for 5 billion years and will continue for about the same amount of time. But it is not eternal. In about 5 billion years, the Sun will begin to expand, becoming a red giant. Its outer layers will stretch out, engulfing Mercury, then Venus, and possibly Earth. A few 100 million years later, the Sun will shed its outer layers and turn into a white dwarf, a small but extremely dense star. But that moment is still billions of years away. For now, the Sun remains our main source of life and energy, without which the solar system could not exist. We began our journey through the solar system with the planets, but now it's clear. Everything in our system is linked and ruled by the Sun. It is a stunning, complex, and dynamic structure where every planet, every moon, and even the most distant comets are connected by invisible threads of gravity, radiation, and stellar energy. Thank you for joining me on this fascinating journey through our stellar system. I hope you have learned something new and gained a fresh perspective on the cosmos. Explore, ask questions, and never stop being amazed. The universe is infinite, which means many discoveries still lie ahead.